the problem I'm going to describe is referred to as a sensor array problem. It's a very common problem in signal processing, though I think most of you people are not very familiar with it. So let me try to describe it. We have an array of sensors. These can be seismic sensor, electromagnetic sensors, or acoustic sensors, and we have sources, which are point sources, and they are in the far field of the array. So these sources radiate spherical waves, and since they are far away from the array, these are planar waves when they impinge on the array, and the array can have arbitrary geometry in the three-dimensional space. Each of the sensors can have the arbitrary directional characteristics, so they can be very, very directive microphones or antennas, or omnidirectional. The sources can be arbitrary. They can be fully correlated, so that one of the signals is just a delayed replica of the other, like when what is called multipass propagation. There's one source which has a direct path to the array, and another is reflecting from some mountain or from some other objects. So the two sources are just coming from the same source, and they have full correlation between them. And we are going to assume that the sources are narrow band, in the sense that we are looking at a certain frequency band, and all the sources have the same frequency, and they have different information, but all at this center frequency. And the problem we want to solve is actually to extract all the information we can about the sources. So we are sampling we are looking at the output of the array. We are assuming that we have, let's say, p sensors, and at each point in time we're sampling a p-dimensional vector. And based on these samples, so let's say we have big M samples, so we sample T1, T2, we look on all this data, and based on that we want to extract all these relevant parameters, that is the number of sources, the directions of the sources or their locations, and the signals of the sources. So all these parameters are actually all that we can all the relevant information in the signals. This problem is very common in as I said, in radar, sonar, seismology. You have this can be in military application. You have one desired signal and one is the jamming signals. In sonar, you might have two different sources. In seismology, two different kind of earthquake and so forth. So this is the same type of problem, and it has also some other applications in different areas. For example, the same problem is applicable to the case where you have different echoes. So you have like several echoes from several replicas of the same signal, which are superimposed on each other. So you have one signal and its delayed version, and they are all superimposed, and you want to know the delays and the number and the amplitude. So all these problems kind of fall into the same mathematical problem, mathematical model. So I don't want to I'll just skim through how you come about the derivation of the mathematical model. You see, suppose you have one source at a certain direction, theta, and this source has a signal which is denoted by S of t. And suppose we look at a certain sensor at a certain point of time. So we're looking at the case sensor at time t. then the signal is going to be the contribution of the received signal, x k of t, is the contribution of this source, delayed and attenuated. So ak is the attenuation caused by the directivity of the sensors, and tau is the delay caused by the geometry. And we're assuming that there is some additive noise there, which represents all the unknown elements in the problem. This can be added, some thermal noise, some interferences. All this is captured by this noise. And since we're assuming that we are operating in a narrow band, you can translate the delay into a phase shift, and so that the signal is simply, and since we can use complex notation, the complex signal, here it's a complex number now, is simply represented by these four. So, and which if you now stack into a vector form x of t, you can represent it simply by this form, where we have just arranged the measurement in a vector, and A is now a vector representing the response of the array to a source from direction theta. So this is the response to a single source, and when you have Q sources, you get just a superposition, and this is a more compact form where we have stacked the vector in a matrix form. So this is our final model. X of t is simply given by a matrix which is parameterized by the directions A of theta times a vector S of t plus N of t. So you see, this is a very, it looks like a factor analysis model, or also a regression model, with the difference that, first of all, unlike the regression problem, S of t is not known. And unlike the factor analysis model, here we have certain knowledge about the factors. So this matrix A, theta here, is composed of columns which are parameterized only by the different directions. So we're assuming that we know the functional form A. The functional form A of theta is known. So this is the very important information which we're going to exploit in order to get the estimates. So let me just give you a geometric interpretation of all this model, which is very essential to the rest of the talk. So suppose, for the simplicity, we have a three-dimensional problem. So our vector x of t is three-dimensional. So this is x1 of t, x2 of t, and x3 of t. And our vector x of t is some vector in this space. And let's draw these the two different. Suppose we have two sources. So we have three sensors and two sources. So in this case, x of t is given by this expression. Ignore the noise for the time being. So in this case, x of t is simply given by a linear combination of a theta 1 and a theta 2, because a theta 1 is a vector times a scalar plus another vector times another scalar. So x of t is simply in the span of a theta 1 and a theta 2. So when there is no noise, x of t is confined to the space spanned by this a theta. So this, from nature, very obvious and natural reason, we refer to this subspace as the signal subspace. So the important observation is that x of t, though being p-dimensional, in case of no noise, is confined to a lower q-dimensional subspace, whose dimension is determined by the number of sources. So this is very important. The x of t, when there is no noise, is confined to some lower dimensional subspace. So what this means, that we can now have a very intuitive and geometric interpretation of our problem. What we observe is these vectors, x of t. So we have kind of vectors which are, it's like a cloud that we observe. And we know that these represent some lower dimensional subspace. They are scattered around some lower dimensional subspace. And our problem is first to determine the dimension of this subspace, which we don't know. And second, the vectors a theta that span this subspace. So this is just recasting the problem in this geometric problem. And as we'll see, our derivation will be based on this geometrical picture. So now, how is this? Well, as I've just described the problem, you can clearly see the connection to this to the MDL principle, or to this general model selection problem, which Jorma was describing. What we have here is data. These are the vector x of t. We have certain vector. Yeah.
Yes. These ideas could be interpreted like factors in factor analysis.
Yeah, they can, but usually in factor analysis you don't have this information. Yeah, definitely. But the point is that here you have, from the physical problem, I mean, you have this information. You can measure it or you can calculate. So what you have is, you have these vectors, x of t, and you have different competing models for these. Every subspace is a model. So you have different models and which you want to fit to the data. And the question is how to choose the best model that fits the data. And according to the MDL principle, you should pick the model that gives you the shorter description of the data. So what we're going to do, we're going to try to use all the different models, all the different competing models, to encode the data. And then we're going to choose the model that gives us the shorter description of the data.
Including the models.
And including the models. Yes. We're going to encode the data and the models, because that's important. So now in order to do the encoding, we need statistical models, because as Jorma stated, all these, if you want to do coding in some optimal manner, you better know, or better postulate some probability distribution, because otherwise you're not going to do the coding in an optimal manner. So we need some models to describe the data, and we're going to, well, there are different models that we can use to describe the noise and to describe the signals. So let me start by describing the models for the noise. One can think of two very simple models. The most simple one is referred to as white noise model. In that case, we assume that the vectors and the vectors and Ti, the noise sample, are simply IID, complex Gaussian with zero mean, and covariance matrix or variance matrix sigma square I. So all the noise at the different sensors are independent of each other and have the same statistical nature. The second model for the noise is much more complicated, in the sense that you assume that, again, that the noise are IID and Gaussian, but this time you're not going to assume anything about the covariance matrix. So this covariance matrix can be arbitrary. So the noise can be correlated and can have arbitrary structure. So these are two different models for the noise. Now for the signals, you can contemplate different models, and again, I'm going to describe only very, very simple one, because even the simple these models are, still the computation they involve is not something that you can handle simply. So more sophisticated models, not Gaussian and others, are probably even much more complex. So for the signals, we're going to have we can have two different models. The first model is I refer to as deterministic signal model. In that case, you assume that the signals, STI, these are the signals that the source is radiate. This is they are some unknown constant. So you don't assume any probabilistic nature. So you just assume that each time the source kind of radiate a different parameter, and its evolution in time is arbitrary. And this is a pathological model in the sense that the number of parameters in this model grows with the number of observations. Every new observation, you have a new vector of parameter which characterize the signals. A more restricted model, though more regular in this sense of the number of parameters, is to assume that the signals S are simply IID complex Gaussian with mean zero and some covariance matrix P. So the signals, these matrix here P can be it can be even rank deficient. That is, the sources can be even fully correlated. So this is type of model that one can apply, and let me just show you what it implies in the sense of the statistical model for the signal. So suppose we have the stochastic signal and white noise model. That is, we're going to assume that the noise is white, that it has a zero mean and sigma square I covariance matrix, and that the signals are zero mean with covariance matrix P. In this case, x of t is simply given by this expression is simply can be easily seen to be Gaussian with zero mean and covariance matrix having this form. So one can, if this is the probability distribution, then because by assumption these samples are independent, the different x at different times are independent, then the probability distribution of the data, big X, is simply given by this product. So the point to make here is that this problem is non-trivial in the sense that if you want to go and apply now the MDL principle, which amounts to computing the maximum likelihood estimator, then you have to solve for the parameter characterizing the matrix R. And this parameter in this case simply you have you have theta is unknown, so there are k parameters. This matrix here is unknown, another k square parameter, and sigma square is unknown, so there's another parameter here. So this is the total number of parameters characterizing these problems. So if k is equal to 2 or 3, I mean, you get a multidimensional nonlinear problem to solve, which is straightforwardly, I mean, it's going to be not amenable to real-time application. So in order to solve the problem, we should try to somehow get rid of the nuisance parameter in this case, which are the covariance matrix of the signal. These are in order to do so, we're going to use this geometric picture which I've previously described. So instead of encoding, if this is the vector xt, suppose we project it on the signal subspace and on the noise subspace. So this is the projection on the signal subspace, and this is the projection on the complementary subspace, which is referred to as the noise subspace. So the idea is to do the encoding in terms not of xt, but in terms of the projection on the signal and noise subspace. So if you know x n of t, x s of t, and the signal subspace, you can recover x of t. So you have two equivalent representation which you can choose according to the simplicity in deriving the estimator. So that's what we're going to do. We are going to compute the description length based on the decomposition of the data into the signal and noise subspace. And the idea is that the encoding scheme is going to be a three-step scheme. First, we are going to encode the parameters theta that describe the signal subspace. Then, using these parameters, we are going to, knowing the signal subspace, we can compute or encode the projection on the signal subspace. So we're going to encode the data given the signal subspace, and then we're going to encode the projection. Sorry, this is on the noise subspace and this is on the signal subspace. So again, instead of encoding the data directly, instead of encoding the data xt, we just encode its projection on the signal and noise subspaces. And for that purpose, we have to encode theta so as to be able to recover the data. So that's how the estimators are derived. And it turns out that if you, we have till 7:15.
Yeah.
Okay. So
Yeah, if you wrap up in 10 minutes,
yeah.
I'll say a few words at the end.
Okay. So I'll finish. Okay. So in order to do the encoding, we are going to assume for the time being that theta is known. Okay. So suppose that theta is known, and we're going to now encode the signal, the noise subspace component, and for that purpose we need a probability distribution for these noise subspace components. And it turns out that because we have assumed that the noise is spatially wide, that is the projection, I mean the different components of the noise are independent and have the same spherical distribution, then a natural model is the following. That is, we have a Gaussian, we're assuming that this vector xn is a p minus k dimensional vector with zero mean and some sigma square times I, some spherical covariance matrix. And if you do it, if you take this probability distribution and you just apply the basic asymptotic results of the MDL you get the code lengths for encoding this data, or the projection on the noise subspace is simply given by this expression. So these two terms here, the first two terms are the log likelihood term, and the second, the last term here is the penalty term, so to speak, which is in our case, since this model has only a single parameter, sigma square, this is the only unknown parameter in this model. We have only one parameter, so this is half times the number of parameters times log n. N is the number of observations. So this is the penalty term, and this is the log likelihood term, where sigma square here is just the estimator of the noise, and Rn is simply the sample covariance. So this is the code length of the noise subspace component, and you do the similar things for the signal subspace component, and if you do the same thing for the signal subspace component, only in this time, instead of postulating a spherical covariance matrix, you just postulate some arbitrary matrix which has k-square unknown parameters. The code length that you get is given by this expression. It's very similar to what you have seen before. The only difference is that the log likelihood term is somewhat different, and the number of parameters is different also because we have k-square parameters in this RSS matrix. So this is the code length of the signal subspace, and now we can combine we're combining the code length of the signal subspace and the noise subspace. So this is the total code length now that of the data, assuming that the vector of parameter theta was known. So that's up to now we haven't said anything about theta. We just assumed that it was known. So this is the total code length of the data, assuming that the signal subspace is known. Now, since the signal subspace is unknown, we have to estimate theta from the data. And following the MDL rationale, what we should pick theta as the value that minimizes the code length. That's what the MDL principle tells us. You should, if you're looking either for the number of parameters or for the value of the parameter, they should be those that minimize the description length of the data. So in this case, minimizing this expression, since these numbers are independent of the parameter, what the minimization amount to is the minimization of these two terms here, the product of these two terms. And well, it can be shown that these estimators, which are just derived by very simple geometrical ideas, can be shown to be the maximum likelihood estimator of the model. The trouble is that to derive the maximum likelihood estimator, you have to go, in this case, through a very tedious algebraic method, because as we've seen in the previous couple of previous slides, the number of unknown parameters is not k, but is k plus k squared. So the maximum likelihood estimator, the naive maximum likelihood estimator, has more parameters than this one. But it turns out that you can get rid of some of them by clever tricks. By this way, using the the natural geometrical picture, you get the result very straightforward. So finally, the criterion for the selection of the number of sources and for the directions is given by this expression. For every possible model, so for k ranging over the possible number of sources, we have to compute this function here, where theta is the value that minimizes the expression that you have seen in the previous slide. And this is simply the sum of the number of parameters in the problem. So this is the criterion, and as you see, it's involved. It involves a nonlinear minimization because theta is to compute theta we have to solve this k-dimensional minimization problem, but still we have reduced considerably the dimensionality of the problem from k plus k squared to only k. Okay, I think I have some simulation results which show the performance of the method and compare them with other methods, but I think we won't have time today.
Well, you might summarize them by saying that the results compare very well indeed.
Yeah, the results. The results of the particularly the detection criterion that I've described is much better than all the other existing detection schemes. And the reason for that is that and I myself have worked out a different detection scheme which is based on decomposing the detection and the estimation problem. So you can, under this white noise model, it turns out that you can solve first the detection problem and then this method combines them. It's a more complex, but the performance is much better. And in certain cases, the previous method that I described, like in the coherent signal case or in the multipass case, other methods just fail.